All right. Welcome back, everyone. First, I want to apologize for the late notice on having to cancel class on Monday. I had to cancel all my Monday, Tuesday classes. Something important came up, as happens in life, that I was unable to avoid. So again, sorry. I always hope that I can give you a little bit more warning, but again, thank you for your patience. But remember that we had said that none of the due dates were going to be affected by that, including the review and the test. The review had already been posted, and the test was already set to go up today, this morning, in fact. So remember, some of this is a little off because I didn't edit this part, but just the availability part. Let's delete that. My computer is being really slow this morning too, which has been fun, which is why I'm a couple minutes late. So you have 20 questions. I actually think I made the test 120 minutes for the first one. 90 minutes is usually what I go with, but for the first one, I'm going to be a little more lenient, and I gave you just a little extra time. It is located in the quiz and test section of my math lab. You really cannot miss it. Let's see. But I'll show you really quickly where it is. And by really quickly, I mean really slowly, because my computer is just dragging. It's awesome. All right, well, while that's loading, let's not do anything. I was going to say I could show you where you go to submit your work. Here we go. Okay, so I just reorganized this stuff. Usually I have the lecture videos at the top of Canvas, but while the test is going on, I put the submit test work here. You'll notice I have a little spot that says submit final exam work here. You can't see that because there's a little green check mark not available to y'all, but you'll just see the submit test 1 work here. That will not be submittable anymore after like 1 a.m. after the test is due. So I said you have today and tomorrow. Today, which is October 7th, and tomorrow, which is October 8th. You have until 11:59 p.m. to submit your work in my math lab. And remember, you're supposed to submit your work on Canvas within 15 minutes. So you go ahead and take pictures of your work, and then you log into Canvas and you upload it where it says submit test 1 work here. So again, your test is in my math lab. Let's hope this doesn't take an hour to sign in. This is us. Like I said, if you go under quizzes and tests, you shouldn't miss it. And there it is, test 1, due October 8th by 11:59 p.m. And I was right, I did make the time limit 120 minutes, which is 2 full hours. Again, if this was an in-class test, I usually do 75 minutes. For the out-of-class, they're generally going to be 90 minutes, but the first one, while we're getting used to things, is 120 minutes. You only get 1 attempt. Please check your work. Please show as much work as humanly possible. This is a no notes, no book, no calculator test. You're supposed to be doing this all on your own. All right, so if you have any questions, you can email me about that or shoot a message in chat. Remember all other homework dates, which I think it's just 3.6 that might be due today. Yes, 3.6 is due today because we missed last class, so 2.1's not going to be due for another week, but that 2.1 will be due a week from today on the 14th because we'll finish that in just a little bit. All right, so back to 2.1. which that little test memo was in the middle of the notes, and I'm scrolling up too far. Oh, there it was. So we talked about the domain, which was which was the list or set of inputs, which we generally relate to x values. X is usually our inputs. We talked about the range, which is the list or set of y values or outputs. And we talked about how something is a function if and only if each input has a unique output. And then the clue for that, for something not being a function, is if you see repeated inputs with different outputs. So a different number going in, the same number going in, and then a different number coming out of it, which we said is kind of like, it feels like the definition of insanity. You know, you process the same thing over and over. Why would you ever get different answers? But relations, mathematical relations, can have that happen due to that plus or minus feature that we discussed. We went over examples of just points as tables of values or delineated by commas and semicolons. domains, ranges, whether they were functions. We talked about if they're equations. The only real condition in this course is if you see y raised to an even exponent, and we did an example. We also started graphing things. We talked about the vertical line test. If something's a function, it can only touch the function once. Each vertical line can only touch the function once. So this right example would be a no. We did other examples. And then the last thing we have on our plate for the day, I believe, is to identify the domain and the range for these three examples. So for graphs, it's not going to let me type. Please don't mess anything up. All right, it didn't. That's a miracle. So for graphs, domain is how far left and right a graph can go. Range is how far up and down a graph can go. You must absolutely use interval notation for this. 5 exclamation marks, super important. So what we're going to do is we're going to take the last 3 examples that we said, are these functions yay or nay, yes or no, and now we're going to talk about their domains and ranges, just like we did with the very first examples where we did domain, range, and whether it was a function. The only thing we didn't talk about range of was equations, and I said it's a lot more complicated. We also said that we were going to table doing domain for functions just to a later section. It's not that complicated, but we're just not going to do it yet, because that's the way the textbook set it up. So again, domain is how far left and right, range is how far up and down. You may need to use a union every now and then, so just be careful. So we're up to example 4. Why does that sound wrong? That's okay. Oh, I know why. I know why. Find the domain and range. For A, we're going to do the same as A before, which was the parabola. So this is our graph, X, Y. It's not perfect because quick artistic skills, but this is just that Y equals X squared graph that we will study immensely. And we already talked about how it's a function because it passes the vertical line test. So the domain is how far left or right that you can go. The domain is how far left or right you can go. So the domain, well, we can go left, we're going left, we're going left, we're going left. See, I'm still going left, I'm going left, I'm going left. I'm also going up as I'm moving along that curve, but I'm only thinking about left and right. And as I'm moving this way, I can go left, and there's an arrow that goes up and left forever, which means this goes left forever, which means that it goes all the way to negative infinity. And we always use a parentheses for negative infinity. So we're going left, left, left forever and ever and ever. Then we ask, all right, well, how far right can we come? So we're starting out this far left, this negative infinity, and we're moving right. We're moving right, we're moving right, we're moving right, we're moving right. Nothing's stopping me from moving right. I'm still moving right, I'm still moving right. And then I hit this arrow that sends me up and right forever, all the way out to positive infinity. So the domain of this graph is everything. The domain is negative infinity to infinity, also known as all real numbers. That's another way of saying that. It's all real numbers. There is no x value that doesn't have an output on this curve. The range, now we're thinking about how far down and up we can go. So how far down we can go, how far up we can go along that black curve. Undo, undo. I can't go down forever because there's no black curve down here. So I can't go all the way to negative infinity. In fact, the lowest point on the graph is right here. Most students really overthink this. You're just thinking, how far low is this? How far up is this? That's the lowest the graph is. What is the height at that point? The height is 0. And now the only time we would use a parentheses here is if there was a little open circle. So if this was an open circle right here saying that we go to it but don't include it, then we would do this. We would put an open parentheses. However, that's not the case. This does not have an open circle, which means it's included. You could actually put a closed point here if you wanted, which is what you can do anywhere along a curve that's included. So because it's included, we bracket it. Now we just got to say, all right, from this lowest height, how far up can we go? Well, you actually have two paths. You can take this left path and go up, or you can take this right path and go up. But the cool thing is it doesn't matter, because whichever path you take, it takes you up forever and ever and ever, higher than I can ever draw. So it goes up to positive infinity. And we can't ever touch infinity, so that gets a parentheses. For B, we're going to go back to the circle, which had a radius of 5, and it was centered at the origin. We said that this was not a function because it fails the vertical line test measurably, or anywhere where the circle is, except for the far left and far right points. But now we're just doing domain and range. Domain is how far left and right you can go. So we're thinking this way for domain, left and right only. So I can't go left out here because there's no graph. There's no black circle there. Remember, the axes are not your graph. This right here is the furthest left point of the graph. And it is included because it was not done like this. It was not done like this. It did not have an open circle. So it's included, so that's a -5, and we bracket it. That's left 5. Now, no matter whether we go across the top path and go right, or across the bottom path and go right, we can move right until we hit this point on the circle, which is +5, and is also included. So that's the domain. The range, now remember range, we're thinking up and down. You have got to memorize that, and it is just memorization. So range, lowest point, well, we can't go down forever. There's no arrow facing down forever. The lowest point is right here. Now, that is not 0. You might say, oh, well, you used these numbers before. Well, those are left and right numbers. Those are x values. Now we're using y values because we're going up and down. So that height is at -5, where this point was. And it is included. Now, no matter whether you go across the left path up, or if you go across the right path up, you're going to go until you hit this point, which is a height of 5. The domain and the range are exactly the same numbers in this instance. Just because it's a circle doesn't mean they have to be. The circle does not have to be centered at the origin, in which case the domain and the range would have different values. Also, I could draw an ellipse, which would be, you know, just like an oblongated circle. An ellipse is something more like this. And then the domain and the range could definitely be different then, even if it was centered at the origin. All right, and for C, we're going to get a little weird with it, going back to C from above. X, Y. All right, so we had this over here at -4, and then this height was -2. Then we had a height of 6. And this is one of my favorite examples in regards to, you probably won't ever see something like this on the test, but I want to do a weird example and test, homework, anything like that. I just want to do a weirder example. And then we'll have this. All right, there we go. Let me make that arrow a little better. There we go. Okay. So this is what we call a piecewise defined function. We're going to be studying them in 2.2. Yes, 2.2. Because it looks like this in one section, and then it's like we just say, oh, no, we're going to now start somewhere else where that open circle point was and draw a completely different looking graph. And we'd have this in another section. It is a function. We talked about how it passes the vertical line test. Even at this vertical line right here, this top point does count because it's shaded, but this bottom point does not count because it's open, so it was a function. If I'm saying things that you've never seen before, that means you need to watch the lecture from a week ago. Okay, so the domain and the range is what we're after. How far left and right for the domain? Well, this arrow says we go left forever, so the domain starts at -infinity. We always parentheses in infinity. Now, from this arrow, we can go right. So now we're considering ourselves moving right. So we're moving right, we're moving right, we're moving right, we're on the graph, we're moving right, we're moving right. Now there's a little pause right here at -4. Now, if this part was not here, let's just pretend for a second that's not there, then the domain would stop at where that -4 is, but it's not a -4. I'm sorry, yes it is. I was looking at the -2 when I said that. Please pardon my my verbal foul. You were stopping at the -4, so without that top part, this would be the domain. Now, maybe this top part wasn't exactly that. Let's say it was over here at, say, a 5, and then we had a shaded point here, and it just went right forever. Now, that would say we'd have to union, because we're going to be skipping this section right here. We stop at the -4, we have to lift our pencil off, and then we pick up at 5, and it would be like this. Now, that's not the example, though. And the reason I compare these two things is very important, because this point did not have the same x values. That's why we had to union them. Now let's go back to the original problem we had. There we go. So we originally stopped at the -4 and then unioned something, but check this out. While the -4 is not included here, when you lift your pen or pencil up to start drawing this horizontal line up here, the first thing you're going to do is make a shaded point at -4, which says that -4 is included. So -4 is actually included for this function, so you're not even going to write it at all, and you won't say, oh, well, that's there, so we do this. No, that would be wrong. We never skip the -4. It feels like we're going to have to skip it due to the open circle, but this closed circle picks it up and then just goes right forever. Whoops, not a negative. Which says the domain is -infinity to infinity. It's everything. Even though there's a vertical gap here, in terms of left and right, all numbers are accounted for. The range, and this is where things get a little weird, and the second part of the answer could be done in a couple different ways, but again, you won't see any homework like this, you won't see any tests like this. Your homework and test problems, instead of this part being a horizontal line, it would be a bendy line or a line pointing up, something like this. This is what you would see homework or tests. But I just wanted to make the example in class a little weirder. Okay, so the range, well, we have this arrow pointing down forever, which says we start at -infinity. Oops, no parentheses. That's supposed to be a comma. I just got it a little crazy with it. And then from this, we're going up, 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 until we hit this point right here. Now, we do have to stop going up here at that -2 value. Notice I'm not saying -4. I don't use this value because that's a left or right number. It's an x value. We must use this one because that's our up or down number. So we stop at -2 because that's an open circle. We parentheses it. Now, in terms of up and down, we do have to skip all of these heights. We're skipping from -2 up to +6. There's no graph vertically in that window. So we have to union it. And then the next height we see is the 6. This point right here, it has a height of 6. So we're going to start at 6. Now, there's a couple different ways to write it. This is one way, because some people say, well, since it's a singular number, just write the number. And if this was a paper pencil test, or if I gave you this type of question, this would be okay. But the best, more technical way to do this, because this 6 is the only height, there's no more up, there's no more down. It's just 6. Even though we can move horizontally, we can't move vertically. The way this should actually look is 6 brackets 6 to say that this is the only number included, and it's included on the left and the right side. So it's a little weird. Again, this portion in terms of the up and down is not something you'll see on homework or test. But when you go to calculus, who knows? Anything's possible. Okay. The last little bit we have is function notation. And I thought I had this in my notes. Did I skip over it? No, that's fine. Okay. All right. I did the bad thing. It worked earlier, and now it doesn't. See, I don't understand words sometimes. Let's try inserting a page, but I'm probably gonna mess this up. Yep, exactly as expected. I don't want to have to do this and merge my notes. Sorry, I'm a little flustered with this. Trying to think of the quickest solution without having to merge files later. And the solution is, I'm gonna have to merge the files later. Darn it. And this is gonna make everything crash every time I open a new one. Whatever. I know you'll have fun laughing with me. Okay, function notation. Function notation looks like this. Without a capital letter generally for us. And then f of x equals blah, blah, blah. So these little tildes are just blah, blah, blahs. That's all I'm saying here. So this is the same exact thing as saying y equals blah, 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 blah. They're literally the same, except that f of x has advantages. There are several advantages to writing something as f of x. First of all, writing it as f of x says it's a function. If you write it as y equals, you would have to say to yourself, well, is this actually a function? Now it says y equals, so you would think that it is, but there can be other y's on the other side when you're dealing with implicit functions, and it's just a lot crazier. So just because it's solved for y, there could still be other y's on the other side, in which case it's probably not a function, but still possible depending on what you do. Sorry, that's me cracking my knuckles if you heard that. So writing something as f of x guarantees it is a function. Unless it's a lie, unless you say it's a function and it's wrong, something like that. So it shows what the input was in the answer. Also, you can put anything into a function, not just numbers. This is not true for y equals blah, blah, blah. Again, those little tildes are just saying like y equals 3x plus 5 would be the same thing as f of x equals 3x plus 5. So again, y equals 3x plus 5, f of x equals 3x plus 5. In terms of, I'm going to say functionality, but I don't mean that word as function. In terms of how it works, these are the same thing. If you want to know what a y value is, you plug in x equals 10 or x equals 12 or whatever number you're looking for. For the f of x equals, if you want to know the output, you plug in x equals 10 or x equals 12. But you will show what the input is by writing it here. So if you want to plug in 10, you'd write 10 there. If you want to plug in 12, you plug 12 in there. If you want to plug in happy face, you write happy face there, and then just turn all your x's into happy faces. This is a very, very, very big advantage because we're going to start plugging in things that aren't just numbers. We're going to start plugging in things like negative x. We're going to start plugging in things like x plus h. And that last idea opens up the entire world of calculus. You can't, or at least you're not supposed to do that when you're writing something in y form. You're only supposed to replace the x with numbers when you're using y equals. So let me give myself some space and just rewrite that. So I'm saying if I wanted to do x equals, let's just do 2, then you would say y is equal to 3 times 2 plus 5, which is 6 plus 5, which is 11. And then you say that's your answer. But in this other notation, if I wanted to find out what happens when x is equal to 2, you would write it like this. Instead of writing x, I write what I'm plugging in. So that's 3 times 2 plus 5. The x still just turns into a 2. The 3 times 2 is 6. The 6 plus 5 is still 11. But I write f of 2 equals. This is the advantage. When you have y equals, your answer only has what you got out of it. But when you have function notation, you can see what you put in and what you got out of it. And my favorite scenario to talk about in class is always, all right, let's pretend I gave you a problem for homework that took you 30 pages worth of work to do this evaluation. So I gave you the craziest function you'll ever see in your life, and I said, find out what f of 1,000 is. And it took you 30 pages to do this. Now, a student who wrote this in y equals form is only going to have the y equals, let's say the answer was 1 as the answer. So they get y equals 1. And then the student who wrote it with function notation as their answer after their 30 pages is going to have f of 1,000 equals 1. So let's say the first student has a dog that eats their homework, a new puppy, and they eat everything except for the last page. So they can see the answer, but I go, well, what did you plug in to get that? And they go, well, shoot, I need to go back and do 30 pages worth of work again, I guess. But the student who used function notation, if their dog ate the first 29 pages and they just left them with the 30th page, they'd have the answer and the input. So when I ask them what do they put in to get that, they know exactly what it is. So that's, again, one of the biggest strengths of function notation, input, output. And again, when you say input, you're talking about x values. When you're talking about output, you're talking about y values in terms of graphing. So f of x is quite literally about the same thing as y. It just has a different appearance, and you can do more things with it. All right, so for our last example, let's evaluate f of x equals x squared minus 5x plus 3. For a, we're going to do f of 4, and then we'll do 4 more after that. Okay, so f of 4. Well, we go equals, and I'll use color to show the plugging in. So f of 4 would be 4 squared minus 5 times 4, then plus 3. See, because the x turned into a 4, the other x's turn into 4s. Again, literally the same thing you do if it said y equals, nothing different. But now instead of writing y equals on the left, you keep writing f of 4. 4 squared is 16, 16 minus 5 times 4 is 20, and then plus 3. 16 minus 20 is negative 4, negative 4 plus 3 is negative 1. If you can't do that without a calculator, you need to work on that. So f of 4 is negative 1. When I plugged 4 in, I got negative 1 out. Now let's do f of negative 1. Back to black. There we go. Now something's going to look a little different. I'm going to do this wrong at first. This is wrong, wrong, in fact, red for wrong. Negative 1 squared, then minus 5 times negative 1, and you can already see what looks a little weird there, and then the plus 3. So the red is wrong. The red is wrong because I'm plugging in a negative, and the negative was supposed to be squared, and it's a multiplying here. This multiplication looks a little weird, and negative 1 squared written this way would be negative 1, and it's wrong. It's not negative 1, it's positive 1, because we're supposed to wrap it in parentheses. Let me just see if I can rewrite it with the blue. So the negative 1, there's no more red in there anymore. Wrap it in parentheses. Wrap the times negative 1 in parentheses. You don't really need the dot anymore with the parentheses though. There we go. And then we just work our magic. Negative 1 squared is positive 1, not negative 1. Don't make simple arithmetic errors like that. Negative 5 times negative 1 is a plus 5. And then plus 3, 1 plus 5 is 6, 6 plus 3 is 9. So when you plug in negative 1, you get positive 9 as your answer. C, we're going to do f of, let me put that just a little lower so I have space. There we go. F of Z, the letter Z, the last letter in the alphabet. That's not a 2, that is a Z. So this is what I was referring. Now that we have function notation, we can plug in all sorts of random things. I can put an apple in this function if I want to. Doesn't mean it's going to make sense, but I can do it. So f of z. So that's going to be z squared minus 5 times z, and then plus 3. Well, these are variables that I just plugged in, z squared minus 5z plus 3, nothing happens. This is actually the answer. So all I did was just turn the x into a z. Remember when we did that change of variables, that substitution method for solving equations? That's kind of like what we just did here, except instead of going from x to from like x squared to u, we just said x is z. Is there any reason to have just replaced the letter with a different letter? Usually no, but maybe your original function was f of t, and you hate using the letter t because it looks like a plus sign. Or it was f of o, the letter o, for some unsaintly reason why anyone would ever do the o as an input variable. And you go, well, that's terrible. I'm going to switch this to, I don't know, a. So you do f of a. There you go. That's all you got to do. So what is the true reason of changing letters and things? Well, it's kind of like when we said let x squared be u. When you want to do a change of variables, and there's a bigger reason for this. So this f of x plus h, there is a bigger reason for doing this. This is the start of calculus. We call this class pre-calculus because it's the class you take before, that's right, you guessed it, calculus. We're setting you up for calculus. So let's do the substitution in blue. So where we had the x and x squared, we're going to turn it into x plus h. When we plugged in the negative, we needed a parentheses for the squaring and for the product. Same issue when you're plugging in binomials. You're going to need a parentheses for the squaring and the product. So I can't just do this. I can't do that. That would be wrong. That would be terrible. I have to wrap the x plus h in parentheses, then square it. Then, with the minus 5 times x, when I turn that into x plus h, I can't do it this way because that looks like 5x, but not with the h. So you got to give it parentheses, and then you have your plus 3 at the end. Now, this is going to be the most involved problem of them all. So buckle up. Here's what people will do, read for wrong. Oh, x plus h squared, that's x squared plus h squared. Just distribute that to these things. No, bad, stop it, wrong. Don't do that. When you have a binomial squared, which you are supposed to do is multiply it by itself. This is x plus h times x plus h. Now I'm going to go ahead and distribute the minus 5. These are separated, so I can go ahead and distribute the minus 5. So I'm going to take this negative 5 and give it to the x and the h there, just so I'm not doing too many things at once. So that's minus 5x minus 5h. And yes, minus because we distributed a negative, not a plus. One slip up and the whole thing's wrong. Then our plus 3. Now, for this bit right here, we need to FOIL the bit that I just put in a little dotted circle. You have got to FOIL that. You might say, oh, that's x squared minus h squared because anything. No, you're thinking of x plus h times x minus h. That would be the difference of squares. There is a formula for this, and I have shown it to you once. It's a squared plus 2ab plus b squared, or minus the 2ab in the middle if there was a minus originally. So we got to FOIL that. So f of x plus h, the x times the x is going to be x squared. That's your f. The outer, the x times the h, is x times h. That's your outer. The inner, the h times x, is hx, but let's keep it in the same order as the other one, just to keep it nice and tidy, because that'll make it more clear that they're like terms. And then for the last, that's the h times the h, which is a plus h squared. That's our last. Then I'm just going to bring everything else down. The minus 5x comes down, the minus 5h comes down, the plus 3 comes down. Now we combine like terms. CLT, combine like terms. So f of x plus h is equal to x squared, doesn't have a like term. You can cross these out as you're done with them. XH and XH. This is like saying apple plus apple. An apple plus an apple is 2 apples. If it was just x plus x, it would be 2x, because 1x plus 1x is 2x. So XH plus XH is 2XH. There's 2 of those things. The h squared doesn't have a like term. The minus 5x doesn't have a like term. The minus 5h doesn't have a like term. The plus 3 does not have a like term. This big, beautiful function is the answer. If you are going on to calculus, you will do that for a quadratic function like the one we just did, I don't know, 20 plus times in that course. And you'll do it a few times in here as well. We will actually be doing this in a bigger problem in a later section, something called the difference quotient. But let's not spoil too much fun for now. So this problem right here, highlight maybe just the D itself, don't highlight the whole thing, but this problem we will be coming back to this style problem over and over and over and over and over. And you know, well, I guess you might not know yet, but you will find out I don't lie. Last one, f of negative x. So again, going back to the original function, let me pull back so you can see it. The x squared minus the 5x plus 3. So we're referring to this bit. But now we're making the x's negative x's. So wherever you see an x, you're instead going to write a negative x. So instead of writing x squared, I'm going to write negative x squared. And because I'm plugging in a negative thing, we wrap it in parentheses. Then we have the minus 5, and now I make that x a negative x. How do I know what to make these? It's whatever that says. It's staring you in the face. Then the plus 3. Negative x squared. Now, some people will really stall out at this, but it's really easy. Just think about the negative squared. A negative squared is a positive, so you actually get the same thing that it was originally, just x squared. All right, well, that's kind of cool, I guess. The second term, the negative 5 times the negative x makes a plus 5x. The plus 3 stays, and that's the answer. You will notice that the answer is ridiculously similar, but not exactly the same as the original function. The only thing different is the middle term was a minus 5x, and now it's a plus 5x. There's something we're going to be doing in the next couple sections called testing whether a function's even or odd. This is exactly what we'll be doing. And the result, if it had been the same, it would mean something important, but we won't do that yet. Just understand that D will pop up over and over and over, and the idea of E will also pop up over and over and over. So these two, while you might think they're the weirdest cases, we have to understand them because we will be coming back to them repeatedly. One more than the other, but that's okay. All right, that will close out section 2. 2.1, I don't know why I said section 2, section 2.1. Here we go. Just ignore all that for a second. Okay. Next section, 2.2. So again, 2.1's homework, you will notice in my math lab, get updated at some point today to a week from today, which will be October 14th. Obviously, you don't need to focus on that right now. Your focus needs to be on the test. And by the way, I was very surprised that I only had 2 students that have really even messed with the review before yesterday morning, Monday morning, excuse me, which is why I've pointed y'all out, hey, make sure you're doing the review. The review is similar to the test. If I notice that hardly any of my students are doing the review, I will make it a mandatory assignment. I might just throw it into the homework grade, or I might make it a prerequisite for the tests. So I might make it so you can't even take the test if you're not going to do the review, because I think that that's important. And I'm not saying that you'd have to earn like 100 on the review, you just have to attempt it. I might make it like a 50 or something. So if all of you students don't want that to happen, please make sure you're doing the review. If you're an A student, you know you're just going to make 100 on the test or something like that, just do some questions after you take it. And you know, in a case like that, it's just usually not the normal. Okay. Rant aside. 2.2, more on functions and their graphs. So we talked about in 2.1 the domain, the range, and whether they were functions of graphs. We said the domain was how far left or right they go. The range was how far down or up they go. And the function test was the vertical line test. Any vertical line can only touch the function once. Well, we're going to talk about more features of these graphs, like where they're increasing, decreasing, or constant, as you can see on this screen. So again, we're setting up more ideas that will be important for calculus. Calculus is the study of change. And increasing and decreasing is the concept of change. Going up is a type of change, going down is a type of change. Constant is, well, not change, but not change is still a type of change. All right, so a function is increasing on an interval if, as you move right, the function is moving up. So something like this. This would be something that's increasing because as I move right, it's going up. This would be increasing. A function is decreasing on an interval if, as you move right, the function is moving down. So it might look something like this, and it doesn't have to be a curve, it can be a straight line. And that's a redundant statement. All lines are straight. This would be a decreasing function. So we're always considering ourselves moving right. There is no left when we're talking about increasing and decreasing. A function is constant on an interval if as you move right, the height doesn't change. So constants are horizontal lines only. But a function doesn't have to just be increasing. It doesn't have to be just decreasing. It doesn't have to be just constant. Functions can go up and then down and then 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 up and then down. This is a sine wave if you go on to pre-calc 2. So it's increasing and then it's decreasing and then it's increasing and then it's decreasing, and this would continue on forever and ever. We won't be doing trigonometry in here. We're usually looking at things like this where we're increasing until we hit this point and decreasing until we hit that point. So we're going to have to use interval notation to describe where these things are increasing, where they're decreasing, and where they're constant. One function may only be one of the three. Another function may be all three of them. Another function may be two of the three. Always use parentheses for the interval notation when you're describing these. Always use parentheses. Don't you ever in your life put a bracket for increasing, decreasing, constant descriptions. There will be no partial credit for that. Brackets are not allowed for this idea. Because when we talk about something increasing, we have to be thinking about what happens around it. So if I'm at the point 0 and I think that's where the increasing starts, I can't say it increases on the 0 because to the left of the 0 it might have been going down, and to the right it may be going up. So that's why you have to use parentheses. Again, there is no partial credit for brackets in this concept. Also, and this is another important idea, you always have to, I don't want to do that with the whole thing, always use the x values to describe the interval notation. Don't even look at the y values. That is the number 1 or 2 mistake that students make with this, is they accidentally throw the y values for these descriptions. But when we talk about where a function's increasing or decreasing or constant, we're thinking about it over the domain, and domain means x values. You don't want to talk about the range because there can be multiple y values, and that's okay for a function, but there can only be a single x value in terms of domain. So that's why you have to use the x values. All right, so for example 1, no, sir or ma'am, why are you doing this to me again? Okay, example 1, my whiteboard never fought me like this. I want you to just describe where it's increasing, decreasing, or constant. So for A, I have this. X, Y, and I'm only going to label a single number on this graph. And that's this one right there, and that's a 4. Let me put it above. So you might say, oh, well, what's this little peak right here? That peak is a 10, or what's this little, what's this height right here? It's a -2. I'm not going to put it in the first example because I don't want you to see them, because you might use them and you never use the y values. So this first example, you're only going to see the x values. So I want you to describe where it's increasing, where it's decreasing, and where it's constant. So a function is increasing when, as you move right, don't ever think about moving left, that you're moving up. Because a lot of people will look at this window right here. They'll look at this window and they'll say, all right, the left side's pointing down, the right side's pointing down, so it's decreasing in this entire window, and that's wrong. It's not the fact that that left arrow is pointing down that says it's decreasing. Remember, you're only considering yourself moving right. So when you start from this far left -infinity, you're moving right, you're moving right, you're moving right, you're moving right, but you're also moving up, 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 up. So we're moving right and up until we hit this point right here. So this is where we are increasing. So we are increasing. In fact, I need to give myself a little more space. Erase, please, and thank you. Well, we're starting at -infinity, which is obviously a parentheses, and then we're moving right, we're moving right, we're moving right, we're moving right until we hit here. Now we still move right, but then we start moving down, which says we're decreasing after that. Now you go, well, Mr. Beckner, you didn't put that 10 there. How am I supposed to know to write that? How would I know that's a 10? Because it's not 10. You don't use y values, you use the x value, and on this x-axis, this value does not need to be seen, it's 0. So we're going up until 0. Now I know that point is included, but I don't care. For increasing and decreasing, it's always parentheses. Never, ever, ever use a bracket for this type of example. Okay, well, what happens as you keep moving right? Well, now we're decreasing, we're going down, we're going down, we're going down, 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 until we hit this point. So in this segment, we are decreasing. So let's start setting up the decreasing answer. Well, we started at x equals 0, which is where it stopped increasing. So we go from 0 until, oh, well, that's the -2 height that you erased, Mr. Beckner. Why'd you erase it? Because you don't use the height. You use x values only. So that's a -4. Now from this point, from this, why did I say negative? Please excuse me, positive. I had that -2 in my head. Now from this x equals 4, what happens to the right? Well, you start moving up again. You're moving up, you're moving up, you're moving up, which means we are back to increasing. But this arrow says we increase forever after that. So we start at the x value of 4 and we go to infinity. But this is back to the increasing. It's a different segment. So we must union it. We start at the 4 and we go forever. And that is the answer. All right. Let's do one more. Second, in case you're still writing that. And for example 2, we're going to do another one that looks like a piecewise defined function, but not as goofy as the earlier one. Okay. But it's still goofy looking. So we're going to go down and left from here. Then we're going to go, oops. You know, this pen has buttons, and I swear they have a different function every time I hit one on accident. So I don't really use them because of that reason, unless it's an accident like you just saw. So we're going to go horizontal from there, and then we're going to go back to going up and right from that. Now I'm going to put a few different values up here. This will be a -5. This will be a +2. Then I'm going to put a -1 there. And then I'm just going to put a 4 up here. All right, so I'll do blue with the increasing. Oh, and by the way, the last one I forgot to say was constant nowhere, because the increasing and decreasing took up the entire graph. So the constant is nowhere. Now, in terms of my math lab, there's an ABC choice for that, I think. It's something like that. It's easy to see. All right, increasing, decreasing, constant. So increasing is where we're going up. Remember, oh, well, this is pointing down, so that's decreasing. Nope, because that's pointing down and left. We are thinking about moving right, and right here is we're moving right, we're moving up. So that's increasing until we hit this point. Let's go ahead and knock out all of the increasing sections. From there, it's flat, which is not increasing, and then from this point, it will be increasing again. So those are all of the increasing segments. So we're starting at -infinity, and then we go up until we hit -1, right? We use this -1. Question mark? Nope. That's the common mistake students make, is that they use the y values. These y values, don't look at them, don't use them. They are irrelevant for this problem. If I asked you ranges, they would be relevant, but I didn't ask you for ranges. So we stopped where the -5 was, so it's increasing until we hit -5. But then we skip a section and we're increasing again, so we union. Where do we start increasing again? Not at the y value, at the x value. So we pick up at 2 with the parentheses. Yeah, the point's included, but increasing is parentheses no matter what. And we go forever to infinity. Now, we're not decreasing anywhere. There's no segment where this graph is going down and right, so it's decreasing nowhere. This is another way of saying nowhere. A circle with a line through it means the empty set. Where is it constant? Well, that's wherever there's a horizontal line, and it's constant here, from -5 to +2. Again, oh yeah, that height is -1, but talking about the -1 doesn't tell you where it's constant. Locations are all about x values, not the y values. That's an important idea to get straight. This is not a complex concept. The answer format is what gets people to make mistakes generally. They mess up their unions, or they'll put the 2 in the infinity first. Or, I mean, even just missing one little -infinity would make that whole thing wrong for the increasing answer. Not understanding what increasing means. Again, they'll see, oh, this down, that arrow is pointing down, so that means it's decreasing in this window. But no, we're moving right, 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 right only. You never, ever move left in a math class. All right. Relative extrema. Relative maxima and minima. These are just different names for the same thing. Extrema. Extreme means the highs and the lows, the peaks and the valleys. Now, there are two types of extrema. There are relative extrema and there's absolute extrema. Absolute extrema means there's a highest point on the graph and a lowest point on the graph, and they're wondering what they are, where they are, that kind of thing. When we talk about the words relative extrema, this word relative isn't just saying what's the highest point, what's the lowest point. It's saying if you were to look at just a small small segment of the graph, is there a highest point in that segment? And there can be multiple highest points in just a segment. There can be multiple lowest points in just a segment. So, and I'm not saying in just one segment, but in multiple segments. So a relative maxima is any point that is higher than the points immediately to its left and its right. That's what I mean by just a segment. A relative maxima, a high, is any point that is higher than the points immediately to its left and right. And there's a super fancy definition for this that I'm not even going to give you, because this is the basis of it. A relative maxima is any point that is higher than the points immediately to its left and right. A relative minima, same idea, but it's any point that's lower than all the points immediately to its left and right. This is the core idea. How do you find relative extrema? Look for hills and valleys. So here's what I'm going to do. I'm going to draw, and I know there's more things to talk about, the last little quotes. I'm going to draw this. So here's a random function, a little more complicated than the examples we'll do because it's got a bunch of bumps. I'm going to do blue for all of the relative minima, and I'm going to do red for all the relative maxima. We're looking for hills and valleys. Valleys. So let's do the valleys first because I got my blue marker. This is a valley. This is a valley. These are the lowest points immediately to the left and right. So here's what I like to think about. If you were to zoom in, if you just, instead of looking at the entire graph, if you only looked at this teeny tiny segment of the graph, so if you zoom in on that little boxed segment, this is what it would look like. Trying to make sure I have everything good enough. It would look like, I don't want to put the axes, in fact, because I only want to see what's in that window. Too far. So if I zoomed in, this is all I see. And if this was the entire graph, that would be the lowest point on the graph. That's what makes it a min. If this was the entire graph, it would be an absolute min. But a relative min is just saying, all right, you go as close as possible as you can. As long as to the left and to the right, those are both pointing up, it's a minimum. The same thing here. If I zoomed in, that picture would look pretty much the exact same thing. And I mean, you can zoom in 1,000, 1,000,000, 1,000,000,000 times, and it would still be pointing up and left and up and right. The relative maxima are your peaks. Peak, peak, peak. They're your tops of your hills. So if I were to zoom in on just one of these, this is all you would see. Imagine if this was on the whiteboard and you went up and put your nose on these dots. All you would be able to see is immediately around you because you're so close to the board. You can't see the forest or the trees, that kind of idea. So again, if you get close enough that that's all you can see, this definitely looks like a peak. There's nothing else higher, which makes it a max. But again, because the graph is really this big picture, these red dots would just be your relative maxes. I'm going to abbreviate with R. Your relative maxima, that point, and that point. And then your relative minima would be this point and this point. Your peaks are your relative maxima. Your valleys are your relative minima. That's it. Now you might say, well, Mr. Beckner, these arrows point down, so wouldn't you just say there's a relative minima at negative infinity? And no, because relative, you're only looking at that window. Infinity isn't something we can actually look at, nor negative infinity. So that's why it's a little unique. So for the problems, after you pick out your peaks and valleys, what you're going to be asked is, where are these extrema located and what are they? The location is the x value, just like how we talked about the increasing and decreasing is based on x values. But the actual maximum or the actual minimum in relative max or min is the y value. You have got to get these two things straight, because if you get the coordinates correct but swap them, if you say it's located at the y value and it is the x value, it's completely wrong and you wouldn't get partial credit. Because these aren't problems where you're doing 5, 6, 7 lines of algebra and crazy work. It's all visual cues and knowing the language. The locations are the x values. The actual output is the y value, which would be the max or the min. All right, so let's try this out. Example 2. I guess I could have typed that because I got a lot to type. Example 2, find all relative maxima, minima, where they are located at. Okay, we're just going to draw a nice little parabola. It's going to go down here. Looks like it's disconnected. Let me do better than that. There we go. That's a little better. And then this height where the bottom is at -8. All right. So we need to find the maxima or minima or all of them. Find all of them, and there can be multiple maxima, there can be multiple minima, and where they're located at. So I said I'd do blue for minimum, red for maximum. Well, here's the bottom of a valley, so that's a minimum. That's a relative minimum. So we have a relative min, and it's located at, now locations are based on x values. It's even really helpful to write x equals to remind you that. If you just say the relative min's located at, I don't know, 20, that would be okay, but writing the x equals is better. Oh, so it's at x equals -8, right? Nope, that's a y value that we see. The x value, we're talking about this point on the x-axis, which is 0. So it's located at 0. And the relative min is, that's the output, that's the y value, that's the -8. Now, do you see any peaks? No, this goes up forever, this goes up forever. So there are what we call absolute extrema, and it would be infinity. But we're not doing any absolute extreme in this course, that's calculus, because it can get a little funkier, if you will. Again, we're only looking for shapes like this. That would be the signifying element that there's a relative max. We don't see any peaks, so that's it for the problem. There's a relative min located at 0, and the relative min is -8. And I can even be a little more thorough, and instead of just saying is -8, I can say it is y equals -8. I meant to do that to begin with. B, another one. And let's go like halfway between the example we just did and the intro example with the lots and lots and lots of dots. Let's go do something like this. And then we're going to turn it, that's a little too wide. That's a little better. And then we're going to come down here. And then we're going to go back up to here and then down. There we go. And I'm just going to label the important points on this because it'll get a little tedious otherwise. So this point right here, this point right here, this point right here, these are obviously our relative maxima and minima. So I'm just going to label them as coordinate pairs. That first dot at the top is going to be 1, 6. The second one at the bottom is going to be 3, -4. And the third one, kind of in the middle, at the far right, is 8, 2. Now I could also ask, where is this thing increasing and decreasing? And it's increasing here and then here. It's decreasing here and then here. But I didn't. I just asked for the relative extrema. So relative maxima, there are relative maxima located at, well, those are your peaks. That's this point and this point. They're located at the x values. That's the 1 and the 8. So at x equals 1 and x equals 8. And the actual relative maxima are, since it's plural, y equals, and I'm going to do this in a respective order. So the 1 had an output of 6, and then and with the 8 that had an output of 2. Then we do have a relative minima, and it's singular, so it goes minimum. The A is when it's plural, the is when it's singular. I don't care if you get the language wrong, but that's still important to understand. Well, this is a valley, so that's where our relative minimum is located, and its height. Those are the 3 and the -4 will both be important. The relative minimum is located at x equals 3, and the relative min is the y value of -4. Again, not a complicated concept. Look for peaks and valleys. What students get wrong is they swap the x and the y values for where it's located and what it actually is. When we talk about locations for functions, we're talking about x values. When we talk about what is the max, what is the min, that's the height, that's the y values. Don't just flip a coin on the test having never studied this stuff. You'll get it wrong half the time. And if you get one wrong, you're going to get the other wrong. And that's annoying, and it sucks, and it's going to make you frustrated. But if you practice this, if you understand how to use the language, you'll get it right every time, because there's nothing complicated about this. All right. We got a few minutes left. So we will introduce the idea of a piecewise defined function. Which we have already graphed a couple of them, at least 2. Which I'll go back and show you what I'm referring to. This example right here would be a piecewise defined function. And the reason I know it's piecewise is because it changes radically at singular points. It's just going up and right, up and right, up and right, and then boom, all of a sudden, snap of a finger, now it's just going horizontally. There's no mathematical function that does that directly without just saying, hey, we needed to be one function where I have my blue marker, and then I needed to be something completely else where I have my red marker, and then I needed to be something completely else where I have this other blue marker. So it's like you get 3 functions for the price of 1, but it's based on where you're located, based on what x value you're using. So if you're using any x values to the left of -5, you would be using the function that described this one. If your x value is anything between -5 and 2, you'd be using this flat function, which would just be the equation f of x equals -1 in particular. And then whenever you plugged in x equals 3 or 4 or 5 or 10 or a million, you would be using this function. That's the whole idea behind piecewise defined functions. When you have something change radically all of a sudden and the previous function, equation, model, whatever, is no longer valid. Kind of like if you were to model how well this country's finances were doing, you would have to have one model before, mid-March roughly, and then you would have a drastically different model once mid-March happened, and you all know what I'm referring to, I hope, where everything just dropped. There is no traditional mathematical function that could describe what happened before and after because of this sudden radical change almost instantaneously. So we need these piecewise functions to describe things like that. Radical changes in a moment. So you give 2 or more functions that you will use depending on what the x value is. Each piece will have a defined interval for which x value to use, for which x value is valid. So you'll have function A for maybe x is less than 0. So if you wanted to use -1, -2, -5, whatever, you plug them into function A. And then you have function B, and it'll say, hey, use this when x is bigger than or equal to 0. So if you wanted to use 5 or 10 or a million or even 0, you would use function B. However, While those functions are only actually true for those defined intervals, you're always going to have boundary values, and it's a good idea to plug in these boundaries for each piece, even if it's not included. So like I said, I said one of them was valid for less than 0 and the other was valid for greater than or equal to 0. So 0 was only supposed to actually plugged into the second function. However, when I go to graph this thing, I would plug 0 into the first one. That way I know exactly where it goes up to and stops, and I just put an open circle there to signify that it's not included. All right, so while I am not actually going to finish or even start this example, I want to go ahead and show you what these look like in function notation. So for example 3, we're going to graph the piecewise defined function. And for A, it's going to be f of x is equal to. So you usually have these curly brackets here, and then it's x plus 3 sometimes, and it's going to be 1 other times. Now, it doesn't always have to be something with x's and something with not. I could have said that this was, I don't know, x squared minus 7x plus 3. I can literally make these whatever I want. Just for this first example, I made it a 1. So the first one is true. We're going to use the x plus 3 for any x value less than or equal to 2. See, this is me telling you when to use the top one. We use this one if I wanted to plug in x equals 0, or x equals -5, or x equals -1,000,000, or x equals 1, or x equals 2, because this tells us where to plug it in. But then if I wanted to use values like 3, 5, or 10, I would plug my x values into this, which you can't even plug in, and we'll get into that next class. And why did I write 3 when I said 2? Maybe I said 3, but I was supposed to say 2. I could make it 3, but then there'd be a gap in the function, and that's not what I'm going for here. It doesn't have to be just 2 of these. You can have these be like x for x is less than 5, and then 3x minus 5 for, I don't know, 5 is less than or equal x is less than or equal to 10, and then x squared for x is bigger than 10. You can have 3, 4, 5, a million of these different things. But in this course, we usually just do 2, maybe once 3. So this is what a piecewise function looks like. Again, it's saying, hey, whenever you're using x values in this window, use the top one, or whenever you're using x values in this window, use the bottom one, except you always plug borders in no matter what. So we're going to call it a day there. That's, we got about maybe halfway through 2.2, maybe 30% through 2.2. Again, don't focus on this stuff for now. Focus on your review and test, because that is today and tomorrow. I will absolutely not give any extensions. If you have any documentation in regards to the test that we've talked about, I did ask you to remind me about that so that we can do whatever it is your documentation says. So please shoot me an email if you know what I'm referring to. If you don't, then obviously you're not included in what I'm talking about. Besides that, have a great day. Study, 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 do well on your test, do as best as you can. Remember, it has to be your own work. Remember, you have to submit it within 15 minutes of finishing the test. The deadlines are absolute unless you have a doctor's note or something like that. So have a good day. This should be up in a few hours, and I'll see you on Monday. All right, take care, everybody.